In this next video, we're going to look at another SUVAT constant acceleration question, but again, slightly different to the first. So I've tried to mix them up in terms of their content. In this one, a skydiver is dropping from a hot air balloon and falling to ground. So again, different from being projected, an object being projected upwards. This is something that's dropping to the earth, okay? As you read the question, he drops for 5 seconds, parachute opens, then he descends for another 10 seconds, and then he hits a constant speed of 4 meters per second. And then he reaches the ground 2 minutes after he left the hot air balloon. So part A just asks us, what was the speed of the skydiver before his parachute opens? Well, we have some information we can use from the question. So if I write my SUVAT again, so I can write in what we know. We don't know S because there's nothing about distance travelled. U was 0 because he drops from rest, which means he had no initial speed. Falls vertically under gravity. Now, this is the interesting thing, because if I just show you a little diagram, he's in the sky dropping this way with U. Gravity is also acting in this direction. So in this case, U and A can be the same sign. They're going in the same direction. So A will actually be 9.8. And T is 5 seconds. That's the time before his parachute opens. Have I got anything about V? No, I haven't, but that's what I want. So again, I've got the same situation, 3 knowns, 1 thing that I need and 1 thing I don't know anything about. The only equation that would work there is V equals U plus AT, and it's quite a nice little thing to calculate there. So V will equal 0 plus 9.8 times 5. So V must be 49 meters per second. So that's part A done. Now part B asks us to draw a velocity time graph for the skydiver's descent. Now this is quite a common question that's linked up with constant accelerations, and we used a velocity time graph to derive some of our SUVAT equations. So let's just draw a sketch of the velocity time graph. Well, we know a bit more information now, so if I just scroll down, B. When you're drawing your velocity time graph, always make sure you label the axes with the correct units, and you put time along the horizontal and velocity up the side, okay? Examiners will penalise you for that. Now we know he started from rest, or she started from rest, and for 5 seconds accelerated due to gravity, and we know that V was 49, so I'll put 49 up here, and I'll arbitrarily just make that 5 seconds there, okay? Scale's not important, but as long as your sketch looks neat and tidy, you shouldn't have too many issues. So that's the first stage of his journey. Then the parachute opened, and if you read the text, it does say 10 seconds, then he retarded for 10 seconds. Now that's basically meaning he decelerated. So when you see the term retardation, that means decelerating until his speed is 4 meters per second. So I'm going to now go down, and you'd expect this, wouldn't you? If you were in a parachute, you'd slow down quite quickly. And there's 4 meters per second, and this was after 10 seconds. So that value 10 seconds later, so that's going to be 15. And the clever bit here, where the examiner did try to catch people out, was he continued at 4 meters a second until he hit the ground 2 minutes after he left the hot air balloon. Now 2 minutes is 120 seconds. Now you can imagine that most people would draw a line along constant speed 4 meters per second, draw it down and call that 135. But remember, the measurement was from the 0 where he left the plane or the helicopter. So that is now going to be 120, okay? And that's all we can do for our velocity time graph. Obviously, use a ruler to get straight lines, but you don't have to be too accurate. So part C then says, determine the height of the skydiver above the ground when he drops from the hot air balloon. Now we've discussed this before in our derivation in videos 1 and 2. Area under the graph is distance travelled. So what we normally do here is we would split our velocity time graph into 3 parts, A, B and C, and then we'd work out the area under each part. So if I look at A, that's a triangle, and formula for triangle, base times height divided by 2. So my base is 5, my height is 49 divided by 2. That'll give you an answer of 122.5 metres. For part B, that's a trapezium, and again, that's partly we're using one of our SUVATs, isn't it? The S equals U plus V over 2 times T. So again, U would be 4 plus 49 over 2 multiplied by the time taken, which is 5. And that'll give you an answer of 10. Sorry, 5 to 15 is 10. That'll give you an answer of 265 metres. Let me just make that a little bit clearer. So there's my 10 there, okay. And then part C is just a rectangle. So that will be 105 times 4, which comes to 420 metres. And obviously the total distance is the height above the ground, which comes in at 807.5 metres. And again, just be mindful, that little trick there with the 120 seconds, yeah, that's something to look out for. So there we go, that's another style of constant acceleration.